So hello everyone, thanks for coming for the next meeting, episode 14 of Warsaw Quantum Computing Group. Today our speaker is Grzegorz Kasprowicz from Warsaw University of Technology, and the title is Open Source SWHW Stack. Yes, is it correct?
Software and hardware.
Software and hardware stack for quantum computing. Okay, so this event is supported by Coodecool, our host. They also sponsor the catering pizza at the end during the after party, and we are also supported by Daftcode, our strategic partner. And I think we can start. So Grzegorz, the floor is yours. Okay.
Thank you. Today it's going to be hard because I'm going to talk about real hardware and a little bit about the software. Because everybody's doing software. When you walk on the street, you can easily spot a guy who's doing software. But if you want to meet somebody who's doing really cool hardware, which works, it's much more difficult. So I will talk. There will be a lot of photos. I will try to keep you awake. So I will talk about physical implementation of quantum computers. We cooperate with several institutions abroad on building hardware for quantum computing. And I will focus then on control systems, because everybody is playing with software, with this Python code, with this Amazon or Microsoft platforms, forgetting that there is a real hardware that does the job at the end. I will mention limitation of existing systems, introduce you to ARTIQ. ARTIQ is actually software, and then there is a hardware which cooperates with ARTIQ. We'll talk to you about some open source hardware we built, and about standards like Eurocrate and MicroTCA. And then again, I'll show you what we can do with Python in building real hardware. Yes, you can build real hardware using Python. It sounds crazy, but this is what we do. And of course, something about the future. So, how to build a quantum computer? There are at least 2 or 3 technologies which are promising. And the most popular one is semiconducting qubits, which has several implementations. You probably heard about Google, D-Wave. D-Wave is actually an annealing process, but it's also superconducting. And Microsoft, topological qubits, they all work in a superconducting regime. Then you have crystals, which is not that popular. There are a few startups trying to commercialize this technology, but so far it's promising, but it's not major. You cannot do really you cannot build a real quantum computer yet. And the ion traps, my favorite, because you can actually see. You can see the qubits. You can take your camera, grab a photo, and admire them. And it's not only reason. They are nice because they work in room temperature. So something about semiconducting qubits, superconducting qubits. I'm not a physicist. I'm not going to explain how it works. What I can tell you is that it's easy to control them. It's easy to build a computer system. Essentially, what you need is a software-defined radio. You need to send a microwave pulse, read something which bounces back, measure the phase, and you get the 0 or 1, and that's it. So, and then you need to multiply by thousands of channels. And the so this is the software-defined radio. We have an analog front end, which sits close to the chip. The modulators, essentially all the electronics which simply converts the software commands to microwave pulses. And once the pulse is bounced back from the chip, which sits somewhere there in the fridge, then you are able to measure the phase. And that's it. It's very simple. It requires just a bunch of cables and a few racks of electronics. The only issue is that each qubit needs dedicated wire. It needs to go down from 300 kelvins to 0. And then if you have 5 or 10 or 60 qubits, then it's fine. You can have 60 wires. But when you need 4,000 qubits, then you need 4,000 wires, which means it needs to grow. and actually the chip is still here. It's very hard to pump it out, to pump out the electrical power out of it, because you can dissipate a few milliwatts maximum. So there are a lot of, you probably heard about Intel chip, which was developed recently, which is going to support a few hundreds of qubits. This is essentially what they need. They implemented this part together with this part and some part of this one into the chip, and then you can have one wire which goes down to this chip which sits on 4 kelvins, and then you have a lot of wires which go to the quantum chip. In this way, you are able to shrink the fridge and multiply number of qubits by thousands. This is essentially what they are going to do. But it's still, the quantum computer based on superconducting qubits will always be the size of the room, will always be a fridge, because you need a fridge to cool it down the chip. And need to cool down to millikelvins. And this is the issue why you won't ever have it in your mobile phone. It will always be as a service connected through some cloud. This is the idea which I like more, because it works in room temperature. Atoms are ions are still cooled down to millikelvins, but the lasers are used to cool down the atoms, but they are in a vacuum. So they are perfectly isolated from the ion trap. And the ion trap can be room temperature. We are cooling down the ion traps only to make vacuum better. Not to wait for pumping half of the year, but to have it done in 24 hours. But for operation of the ion, you don't need your low temperature. How it works? Well, there is some magic. Essentially, you need a few lasers. Something. Oh, this is how the ion trap works. From some old slide. There are several types of ion traps: linear, 2D, pole trap. Pole trap is nice because you have ions which rotate, and the force during rotation forms a crystal.
Do you need vacuum?
Yes, of course you need vacuum. In both cases you need vacuum. But for superconducting qubits, you need vacuum only to improve cooling, while for ion traps, you need a super high vacuum to minus 13 or 14, where if you want to measure such a vacuum, the best pressure meter works up to minus 13, or you are at the edge of the measurement technology. But I will show you later. You can buy the ion trap processor, which is the size of the Pentium chip. I will show you later. And so there are several types. This is linear ion trap. This is the trap here. This is the trapping zone, and this is the operation zone. Then you have some wires. There is also other kind of trap. This is trap, I think, from Sandia. This is from Innsbruck. There is one from Oxford as well. Essentially, what you do, you have a bunch of ions. This blue and violet, they are laser beams. So this is just light. You have a bunch of ions. You need one beam which affects all ions, which uses Doppler cooling to chill down. It's quite interesting how this chilling works, because when you have an atom, it moves. Yes, it vibrates quickly. And so it has and atom can absorb energy if you enlight with the laser. But the absorption window is very, very narrow. It's a few hertz. So when your atom moves one way, there is a Doppler effect. So it doesn't absorb, and when you move back, it absorbs. So just through shining the laser on it, you are able to provide energy one way, and so it actually extracts more energy than it absorbs, and then it cools down itself. Just by shining the laser, you cool down to millikelvins. You need something more. If you want to change the quantum state or to read the quantum state, you need a few more lasers. One laser is to simply you can imagine you can simply rotate the atom Yes, using this block sphere, you can rotate the quantum state. So you can use one laser to change the state, and you can use another laser to read this state. To read this state, you simply use two different wavelengths. You can use either as many atoms, as many lasers as the number of qubits, or you can use one laser and a multi-channel optical modulator. To read out, you can use either CCD camera, or you can use multi-channel photomultipliers. What's nice thing about this technology is that you can make it small. At the moment, the ion trap is size of the Pentium processor. The only thing which is big is optics. I mean, you need to provide as many modulator channels as the number of qubits. And you need to provide as many detectors. So you have one trap and then a huge bench with mirrors, optics, wire fibers, etc. But it changes. You can attach photonic chip on the top of the trap, so which has all the optical routing. This is the technology which is the most promising, and once matured, will enable miniaturization of ion traps. And this is the technology which sooner or later will be in your laptops. So now you have a GPU, and then you have a QPU, or whatever they call. And this we are working on. How to scale the ion trap? It's easy to have 100 qubits, and it's quite easy. IonQ already has something like 80, and then managed to entangle 60 of them. So it's not an issue to trap ions. It's already working. If you want to have more of them, existing traps, you cannot extend the length indefinitely. The ion trap computers have one nice feature over superconducting ones, that you can make full mesh. I mean, entangle every qubit with every qubit. Not like IBM does, that you have some groups of 6 or something like this, or D-Wave, like they have groups of, I don't know, 4 or 6. So D-Wave essentially is like you buy 8 Commodores and claim you have 64-bit processor. Yeah. Sorry?
Not anymore, the topology has changed.
Yeah, but it's not, you don't have full mesh. You cannot explore full potential of quantum technology. You cannot have full mesh and 4,000 qubits entangled together. It's going to change sooner or later, but at the moment, this is the only technology which provides full mesh interconnectivity. How to scale it up? You can connect them using fibers to have more, to be able to process the quantum state from one qubit to the other. But this is very inefficient. I mean, you lose 99.99% of photons. The other idea is to use 2D, charge coupled device. You are working with Oxford on this technology. Its control of this topology is very challenging. You need to have very, very low noise electronics. So when you move the charges, the qubits, they won't heat up. So, a few words about realization. This is how the nowadays quantum computer looks like. Essentially, it's a room still. I mean, this was this photo taken at NIST. They're actually not working with quantum computers. They are working with metrology, but the lab looks similar. So, one of the issues with development of quantum computers and quantum technology is that each lab uses unique instrumentation. They build their control module themselves. They pick random boards from AliExpress, some Raspberry Pis, add some development boards, uses a lot of chewing gum and tape, silver tape, and they do something. And then another lab wants to recreate the measurements, for example. They have to build similar setup or use similar setup, and there are lots of problems, and it takes years sometimes to recreate essentially the same conditions. So this is example of a development. I was a few years ago. I was with GILA. It's a quantum lab in Colorado, in Boulder. So I was visiting a few labs. There was a lab tour after the conference, and there was in every lab some poor guy was building its own DDS. DDS is a direct digital synthesizer. It's essentially a piece of hardware which lets you generate well-defined signals, not only sine wave, but just signals. And it's used to widely in all types of optics and quantum computing and quantum sensing. So every poor guy was building its own. I was asking, why are you building your own DDS? Well, because, well, there are some on the market, but well, not well documented. They have some issues. I don't have full documentation, so he's building his own. And then the PhD student leaves his not finished, somehow working board without documentation, and its process repeats over and over again. So this is how the ARTIQ was born. So a few guys at NIST were simply pissed off, and they said, well, it's time to do something. They contacted one geek, a guy who developed a high-level programming language, which is called MiGen. And so with this language, you are able to describe complex hardware, including sub-nanosecond determinism and very short latency. And so they created a control system with some tools, debugging tools, some drivers, and then they ended up with, okay, we have a nice software, but we still lack hardware. So they contacted me. I had a few projects already done for CERN. You probably know what CERN is. It's this Large Hadron Collider and similar toys. So we did some open source hardware for them, and then I said we started building the hardware. And so we defined, we already were using micro TCAE standard, we were using compact PCI serial standard. So based on this standard, I built a few boards, and then they wrote a nice software for these boards. And what we did, which is unique in this open hardware environment, I mean the world, is that we commercialized these boards. I mean, we found two companies who managed to take our designs, polish them, do right testing, build test benches, which they managed to write manuals and provide support. This is challenging. And once we did it, I think the idea, we realized this is a cool idea because it works. So the hardware, as I said, is based on micro TCA. It's old slide. The number here is not valid anymore. So we have built at the moment there's over 50 different devices. They are not cheap toys. The average price of one module is something like €1,000. But it's still a few times cheaper than similar performance hardware from National Instruments or from Zurich Instruments or from other instrumentation technologies which do things for science or for quantum. So our hardware essentially fulfills certain applications, which some of them are dedicated to quantum needs. Some of them are general purpose. You can use them to play MP3, of course, but it's not the best application for these devices. But they perform much better in, let's say, controlling shifting qubit in a ion trap, or stabilization of magnetic field, or removal of laser noise, etc. And as I mentioned, most of the hardware is already available. We already sold over 1,500 modules during last 2 years, essentially. These are the institutions in the projects. There's not of them, they are the most active ones. You can see the NIST, who was who gave the idea, and then there's University of Maryland, with whom we signed the first contract, And then there was University of Oxford, who is the most active user and developer and tester of this hardware. And there are lots of other companies, institutions around the world. At the moment, there is over 80 institutions around the world 80 labs around the world who are using this hardware. Okay, something about hardware finally. So this is how the hardware architecture looks like. So we have, we call it Cynara. Don't ask me why, the story is long. We started calling our modules, we were looking for some idea to how to call the modules, not to make these names short and which they are easily recognizable. So guys started calling them the Russian lakes. I don't know why, nobody could find a better way. But at a certain moment, the easy names just finished. And they started inventing like Novogorny or something like this, which was unacceptable for English-spoken users, English-speaking users. So then we started doing the mixture of the names. So sampler is something which samples. And then there is a shuttler, it's a module which does the ion shuttling. And then there was Zotino, which was slow digital to analog converter. Now we have Fastina, which is fast version of it. So now it's a total mixture of names which don't say anything, but they are unique at least. If you Google Fastina, you have one board and that's it. It's easy to find the documentation at least. But well, Stamper, for example, which is stuff which do time stamping, etc. So essentially, what we have a computer which has a standard Ethernet link, which is not deterministic. And then we have standard crate. This is micro-TCA crate. Micro-TCA comes from ATCA. ATCA, some of you maybe know, it's advanced telecommunication, something like that. And this micro-TCA is micro-ATCA, which means it's micro something. This name doesn't mean anymore what was supposed to mean at the beginning, because this evolved to the standard for scientific instrumentation. If you go to DESY to visit the accelerator, we see a lot of these crates. It's like National Instruments stuff, I mean this ecosystem, but it has several more advantages. First of all, it provides the way to synchronize all the modules with some sub-nanosecond accuracy. And you are able to synchronize several boards with some sub-nanosecond accuracy. And then you have a full mesh connectivity with dual star, with redundant links, lots of interesting stuff. So far, this was used only for accelerators, but this quantum computing is, we found that it's perfect for quantum computing because it wasn't designed to be for quantum computing, but by chance it fits ideally to the requirements of these systems. You can need a lot of channels, fast channels, precisely synchronized together with high-speed links, and it has all we need. But it's quite expensive. The crate itself, the box is 20k euros. The controller is another few K, and power supplies, everything makes you easily end up with 30k just for the chassis. But you need this sub-nanosecond accuracy only for part of your project. When you need to shuttle the qubits, when you need to generate several signals to, for example, for your superconducting computer, or when you need to precisely align several channels for segmented track control. So we invented something cheap. This is Eurocrate. The second application, when it's used, there are musical synthesizers. If you like techno, you can easily buy such a modules which generates all these beats and artificial sounds, etc. So we use this standard. The crate is 50 or 100 euros, and we are using this for all non-critical applications. I mean, for non-critical, but the ones which still require 1 nanosecond accuracy, but don't provide that precise channel alignment. So you have a FPGA controller in one of these slots, and then you have backplane or ribbon cables, which you simply connect several such modules inside. So you have both high performance, costly, modules, and you have also low cost, slightly lower performance, but they are something like the crate is $100 and the modules are 1K or so. So you can have an entire chassis with full of boards just for the price of empty micro-TCA chassis. So these are some pieces of hardware which we did. Some of them are very complex. You can see the traces. There are 16 layers. It's just not easy to use. It's not enough to simply draw, because if you simply draw or let the program draw it, they won't work. If you see this lane, for example, this trace goes over here, and here. It transfers the signal at the rate of 16 gigabit per second. And if you do stupid mistake, simply make this hole 0.1 millimeter too big or too small, the signal won't pass. It will simply stop here and reflect back. The only way to spot such issue is either to build the board and simply say it doesn't work, or simulate. You have powerful tools like hyperlinks, or another one from ANSYS, Scywave, which are able to actually check if it runs without building it. And this is one production cycle of this board is something like 30 kilo euros, so it's quite expensive. And if you, without proper analysis, you can simply build and discover it. You can throw it to the rubbish. So these are the applications for these modules. We call it Eurocard extension modules, simply EEM, because it's simpler. So these are, as I said, this is for slow control. You can buy small crate, big crate, double crate. This is the controller. These are the IOs. These are low-speed DAGs. There are high-speed digital synthesizers. There are high-speed IOs. There are some camera inputs. Lots of other boards. At the moment, we have over 50 of them developed. Something like 30 of them are already commercialized. And you can buy from the market. That's why we call it COTS. I mean, it means commercial off the shelf. And other modules which you can see, which were developed. Actually, some of these modules were just master theses of my students. Some of them were engineering theses. They have one student who is doing a master thesis on very complex module for shuttling ions. He's defending the thesis tomorrow. We have a few grants. That's why I can pay my students for the job they do. And other modules, we have also, if you like Raspberry Pi or Arduino, there's one module especially for hackers. You can plug your favorite module here and integrate together with the rest of the control system. So you can put your Arduino here, which you like, which you know, and we have a special driver which integrates with the rest of the system. And then you can simply do your stuff you like, and then, or you can even use it to control the rest of the system from your Arduino if you really want. There could be some niche application when you would like to do so. And this is another type. This is example of commercialization. One was commercialized by one company, it's a Technosystem. Another was commercialized by Creotech. So they have two different colors, so client can easily distinguish which one is which. This is example of a box which was quite successful. Recently there's somebody who ordered over 100 pieces of them. So each of them is 8 kilo euros. If you want to buy something similar from mini circuits, you pay 3 times more and you don't get any diagnostics. And here we have Ethernet, you can connect, you can measure or then monitor all the parameters. If you have hundreds of them, if you build 1,000 qubit computer, you need a lot of them. And if one of them starts failing, you can easily discover new physics. This is how it happened. Do you remember the case when some scientists from CERN claimed that Einstein was not right? Yeah, so it was a loose SMA connector, which transfers the signal from the GPS receiver to the cavern, to the detector 100 meters underground. my colleagues, actually they were my students at CERN. There's a strong group of Polish guys who developed White Rabbit standard. Maciej Lipiński, for example, Tomasz Wostowski, maybe you know some of these names. So they installed this White Rabbit system and said, oh, there's something wrong with this timing. And then they discovered that there was this cable. So this is how, there's some photo which is missing. There are some examples where this hardware is installed. This is somewhere this is in Maryland, this is in Nice, this is in Oxford, I think. This is in Warsaw, and this is the piece of quantum computer Oxford is building. So essentially, to have a ion trap quantum computer, you need simply a few of these racks. They're just standard server racks. You have optical tables. The mess you saw in one of the first images, now you can simply enclose to nice sealed package, which you plug to the chassis. You connect fibers, you connect control cables. This is my electronics here, which we built, we delivered to Oxford. And then you have several of these optical tables enclosed to the rack. So now it looks like a part of server room.
Vibration isolation.
Well, yeah, of course, you cannot put it in the ordinary office. It won't work here. You need to have a building with dedicated sandy band. The ion trap must be installed on optical table. These optical tables, they have already dampers inside. So they are resistant to some extent isolation, to the vibration. Now, something for easier and more familiar for you, we'll talk about software. How you control such complex hardware? Well, we used ARTIQ. It means advanced real-time something for quantum computing, for quantum. We use Python, but it's not usual Python. This is something standard. Yes, you can, but this is the highest level. Imagine you want to simply fire the laser for 20 nanoseconds. In the same time, you want to fire the optical modulator, generate 5 pulses of it. This is the highest level of Python looks like. This is a library. You simply put these commands, and that's it. And it does all the magic. And you use standard tools, standard libraries to draw images, to take this actually does these are, I think these are ions photos. You can take grab. Oh no, it's not the measurement. There I have another idea, another slide with image of photons of ions from the camera. So this is how it looks like for the end user. But what's under this layer? This is what is under. So we have a GUI, or you can use command line. There is a Git repository and all the standard file systems where you keep all these experiment files, logs, etc. And then you have this magic FPGA device connected with all the submodules, which can also have FPGA with using real-time I/O. And each crate has some kind of this core device. You can also connect standard equipment using USB or some other other interfaces, which is not necessarily when you don't need a high-speed control. If you simply need to turn on cooling, you won't use a sub-nanosecond link. You simply plug it to the outlet, yes, or using some form of controller. Let's go deeper. Let's start from the lowest possible level. Does anybody of you played with FPGA or VHDL, hardware description language? Maybe, or doesn't look so. Some of you may play. It's nice when you want to build blink LED, but if you want to implement a 100 gigabit transceiver, you can lose all your hair and contract some illness, mental illness. So essentially, you can do, this is blinking LED, simple counter, written in VHDL. You can make it simple. Simply install Quartus, open the graphical user interface, grab the counter from the library, put it to the workbench, connect the signals, and press compile. It will do the same. It works to some extent if you do simple things. If you do more and more complex things, you have more and more schematic pages and usually end up with mess you don't control. So that's why people use VHDL or Verilog or some high-level synthesis when the entry is C++ or C. We are using Python. This is exactly the same, almost the same example. This is written, look at the number of lines, that I preserve the same spacing. That's why we use Python, because you type it much faster. You don't put unnecessary things, because most of these things like this are simply not necessary. They simply don't provide additional information to the compiler. They are here to keep compatibility with this VHDL that was developed for some completely different purposes 40 years ago. We are using because there was it was evolving evolution. There was evolution of this language, which was finally adopted to the FPGA needs. It was originally developed to describe ASICs and ASICs design process, etc. So we use Python. Simply, and this is not all, because this is just the logic. You need an additional file which describes the board. It's also, here it's simple. You simply import the platform, define that you want to use the feature of this platform, which is user-led. You simply implement the counter, and that's it. And it blinks. You choose 25th bit of counter to control the LED. And this is some graph showing difference between where the ARTIQ is. You can either describe this FPGA with a VHDL, or you can use Python as an interpreted language. This is between. You can do both. You can use this Python to describe hardware. You can also use it as an interpreted language, and you can also use it to build so-called core devices where the Python is translated to low-level machine code executed on one of the processors. So this was the lowest level. So you simply describe how the gates are connected. You can use Python, for example, to write your own processor. Then you have MISOC. MISOC is another tool. You simply take, which is the tool which lets you manage and build digital circuits. Imagine you want to build your own computer. You take CPU, take registers, take some memory, take some user interface. And this is the code which describes such architecture. This is all you need to provide addresses where the peripherals are connected to configure. This is the place when you plug your processor, this you plug your wishbone bus, this you plug your GPIO, just one line, one line, one line. This is all this entire architecture. Compile, download to the FPGA, and then you can run your own code on it. Assembly code. Or Python code, but it needs to be compiled and translated. And this MISOC is getting more and more popular. It's still niche, because the learning curve is quite steep. In my company, I started encouraging people. They were simply pissed off for first month, but then they loved it. They cannot leave it.
How about chisel?
Oh, no. I heard about it, but we don't use. We are doing a lot of development for this ARTIQ community, and that's why we stayed with this, which works. And this is entirely open source. The chain is open source. The libraries are open source. It's a great tool if you want to build some cryptographic devices, because every aspect of the toolchain is open. Of course, in the end, it produces VHDL, which needs to be synthesized. But there is one path for one family of devices from Lattice, where entire chain is open source. So from your top level architecture to the bits, you control all the process. So if you want to build something for military or for your own security, you can use this toolchain, because you are guaranteed that no sniffing part of code would be implemented by the tool vendor. Oh. Okay, let's build the quantum computer then. We know how to how to describe the hardware. We know how to build the control system. So this is where the ARTIQ and MiGen sits. When to build the control hardware. Then we can use Python language to implement universal gates. And there is one layer which is still missing, and we just apply it for a grant to develop a quantum compiler for this architecture. Essentially, what you need to scale such a computer, so you need for 80 qubits, you need something like 5 racks full of hardware. For the moment, once we switch to the ASICs, we'll be able to fit it to just size of maybe not pocket calculator, but the size of standard PC. So this is the software, this is the photonics, this is the control hardware we develop. Need some explanation, or simply we can go to another slide? So this is essentially this is the star micro TCA part. When you have a controller, you have clock distribution, you see the Baikal name, and then we have several modules. This is for high speed, well aligned, well synchronized outputs, and here are low speed solutions when you can either directly control the modules, or you can use Ethernet FPGA controller to control the modules. So this is, we can connect this module, this crate, in several ways to achieve what you need. Something about distributed real-time I/O. I don't want to focus on it. Essentially, it's a protocol which is designed especially for this project. It's based on White Rabbit. White Rabbit is a time distribution. Maybe you've heard about PTP, Precision Time Protocol, or IEEE 1588. So it's an extension. It uses standard Ethernet. You can run YouTube on a White Rabbit. Of course you can. And this hardware costs slightly more expensive than PTP switch and PTP nodes. But it's not deterministic because it's Ethernet. So we took the White Rabbit, we took the clock synchronization and frequency and phase tuning from White Rabbit, and we changed the protocols. It's not Ethernet anymore. It's some deterministic protocol. It has very low latency. It adds to 200 nanoseconds per switch, of course, plus the fiber delay. And you can build spanning tree configuration. And this is example. This plot is not easy to describe, but essentially it's a phase noise. It's a phase noise. It adds a jitter of roughly 100 femtosecond RMS in a 20 megahertz bandwidth. Something about who's using this. There were 2 surveys performed by guys from NIST. So there were how it was in 2017, 2018. They didn't perform any survey in 2019, unfortunately, so don't know. But at the end of 2018, there was 80 laboratories who were using this stuff. And now I think much more, but I don't know the precise number. How to compare our control system to other? There is the most popular one is LabVIEW, which does not give any RF features, no synchronization. It has only triggers. It's quite expensive. It's closed, and it doesn't have any path towards ASICs. Zurich instrumentation is nice and beautiful, but it's highly expensive. It works. It has a very good user interface, provided you don't want to do anything non-standard. If you want to do some simple fixes, you pay a lot for engineering testing, which is good for some users and which is bad for some users. And there are also ARTIQ and SNAR, of course, has all the advantages until you start using, because the learning curve is quite steep. The LabVIEW is really plug and play and works. We are working on it. We are now preparing the cloud service to ARTIQ, so you simply have a LabVIEW-like user interface. Simply plug the modules and you have a demo working in an hour. Not within 1 month, because all the tools setup would be provided as a service. So this is idea we're working right now. We want to launch it on Quantum Conference in US in June. So we are working hard to make it happen. We have a grant for it, so I think we'll manage. And yeah, this is the chip which Intel does. This is the ion trap. This ion trap, this is the size of Pentium processor. You can buy it commercially from Cold Quanta for 100 kilo euros. Essentially what you need a bunch of lasers and optical modulators. But the problem is that the one optical table, it's this size, 19-inch rack. But this is project we are working on. We are working with Ferdinand Braun Institute from Germany. This is entire optical table, but it's a size, you see this the paper clip, this is the size. So with these optical tables, let's say, and you need something like 20 of them to make simple, useful quantum computer. Quantum computer which does not need error correction. Because with ion trap, ions are nice qubits because they are ideal. They all have the same number of protons, neutrons. They are all ideal. You can't have half ion of the same species. So the ion trap quantum computer is as good as lasers are and as electronics is. And we are working on the ASICs in such a way that some of the modules which are now this size will be packed to ASICs. And then you can plug several ASICs to one board like this and enclose with ion trap in one chip. And then, of course, you have this laser, but you need still optics. And then you have photonic chip which sits on top. And then you have a quantum computer this size with lasers, everything. This is the future which will happen, I don't know, 10 years. Yeah. So we are working with CERN on standardization of the equipment because the equipment was invented for this quantum just by pure coincidence. And then CERN wanted to develop its own standard for accelerator instrumentation. And we started talking and said we were trying to build almost the same stuff. The only difference is they use backplane and we are using cables. Why not to redefine? So we design adapters that you can attach to our board and use in CERN backplane. So this is what we are doing right now. And yes, and now we are essentially applying for a grant. We want to build the ion trap in Warsaw next year. Hopefully if we get one. And we started building ASICs. So I think we end up with time. Okay, so I want to talk about open hardware. That's the last topic. You know this. You see this penguin. It's modified version to describe open hardware philosophy. Open hardware is quite different from open source because if you want to make a copy of software, you essentially pay only for the internet transfer, and that's it. In hardware, it costs. Every improvement costs. Every board print costs. In case of complex boards, every iteration is maybe something like 30 to even sometimes 100 kilo euros. So it's quite expensive. Of course, if you build something Arduino style, you can solder at home. But if you do something with recent FPGAs, when one chip is 100K, so well, it's painful to do some mistakes. So you need a lot of expensive tools for verification of the hardware. So this CERN created open hardware license. It's called CERN OHL. I can proudly say I was one of the first guys who was testing this license, who was building this White Rabbit modules. And so we can have non-commercial open hardware, which you have a lot of them on GitHub. A lot of random boards. You can they're simply there. You can download. You don't know how it works. Nobody did the right characterization. Simply, it's not scalable. Nobody was applying right engineering tools to test them. You can have proprietary and non-commercial. So, well, it's not reusable. It's dedicated to some very, very specific stuff. Like scientists are building non-commercial proprietary hardware, then the one scientist leaves and then they have to redo it over and over again. Of course, proprietary and commercial, which is nice. When you buy it, it usually works. If you have some issues, you have to rely on the provider, which is normally, this is this laptop, which is proprietary and commercial. But if you are building long-term project, then the company may stop existing. And then after 2 or 3 years, the spare parts are not available anymore. You have to throw it away and buy a new one. So commercial and open, it's the best of the two. You can have open source. You can buy it. You know what you are buying because it's like any other product. And you have a group of developers who actually, in this case, from the point of view of the entrepreneur, who do the R&D for free. It's sometimes enough to give some parts, some nice design. You probably heard about HackRF tool, which is open source SDR platform. Some of you may know, some of you may don't. If you want to make your own BTS, 5G or whatever, you can buy for $200 platform attached to antennas, run the software. You are now a telecommunication operator in your room. So there are nice examples. Raspberry Pi used to be, but they eventually closed the sources. Arduino is kind of open source and commercial. There are lots of companies who are cloning them, but the quality, if you want to high quality, simply go buy original from Arduino. In case of our hardware, nobody ever tried to copy because, first of all, testing requires a lot of know-how, and nobody would buy something none of the scientists would buy something from non-trusted vendors. And the other thing, if you build it yourself, it will be more expensive than to buy. Because we have completely different prices if you buy 1,000 FPGA circuits than if you buy one. It's 5-6 times cheaper. So even though we earn quite a lot on this hardware, it's still cheaper than to simply grab the file, go to assembly house, and ask to build a few pieces. So I think we can summarize. This is an example of successful open hardware. The sales are growing rapidly, and we are working on a better and better software. And I can say that if you want to commercialize open hardware, you have to give the user a choice. 2 companies, it's a good number because they can compete with quality, and they can the market is still big, so both companies can make profits. And so if you want to play with it, if you want to join our group, we are open. We have a nice lab in the center of Warsaw, at the Warsaw University of Technology. So we have, at the moment, there are over 20 people in my lab. And we have also one of the company who is commercializing this stuff is mine, and the other is some other one in Piaseczno.
So what are the names of companies?
Creotech and Technosystem. So if you're looking for an interesting job, there are some open posts still in Creotech. They have R&D office in Ursynów. Yes, so people to make commute better. Okay, so thank you.
Thank you. Very nice talk.
Questions?
Do you have any questions?
Yeah.
So what do you plan to do funding of your ASIC?
Well, so we are working at the moment on architecture. They have one PhD student from microelectronics department who is implementing a few ideas in just using Verilog and ARTIQ on just standard process. We want to go for FDSOI 28, which is a well-characterized process. It works in cryotemperature. And we planned, once we know what we want and what technology is possible and what is feasible, we apply for a grant. There's a lot of money lying on the street if you do quantum. And there is, yes, really, if you say you are doing quantum, you get immediately investors, American investors knocking to your doors, simply saying, take my money. because, well, this quantum bubble is still here. Yeah, so the satellite bubbles almost popped. Now people. Yeah, yes, of course. There is one. Yes, there is 1 billion of flagship money. I'm actually Polish. I'm representing Poland in European community as an advisor together with Professor Kuś in a quantum flagship. We have a meeting next week. So there will be 1 billion, and then there is this high performance computing money, probably something around this money which will be shifted towards quantum to boost this.
No, it won't be, because I'm on that.
But there are plans to shift. Yeah.
To include quantum into HPC.
Yeah, exactly. Yes, so it will include. But anyway, this money will be spent on quantum. Yeah, this is exactly what I meant. So probably we met in Helsinki last. No? Yeah.
It's good to hear that because so important people here.
Yeah. So
take advantage of that during the after party and ask questions.
So yeah. So there's the future is bright, and I think we are in the right place. Actually, during the gold rush period, there was such a proverb that don't sell, if you want to make money, simply sell showers. Yes?
Levi jeans.
Or level jeans, exactly. When gold rush sell showers. And I'm simply changing this proverb when quantum rush sell control systems. Yeah. So this is actually, it seems to work. There are more and more startups which are coming, but so far all of them are focused on superconducting stuff, which is, I think, as I said, you simply need 2 wires to send and receive the signal, and that's much easier to build the software. We are focused on photonic, which is not only quantum. Quantum is something like 5% of it. Most of the people are buying for neutron atoms, for Bose-Einstein condensate, for some metrology, for optical clocks, etc. So there are more and more people who, the 5% of institutions, not sales, which are just quantum computing.
Could you show the switch again?
Which one?
No, the switch is closer towards the end of the talk. This one.
Huh?
So if it's switch, what sort of radix does it have? How many channels?
Well, in our current implementation, it has 12 channels, one of them, and second one is, this low cost is 4 channels.
What's the bandwidth?
5 gigabit per second. The link speed. The bandwidth is much slower because it's not optimized for speed. We don't need that fast transfer. We need low latency and we need precise timing, so it's fully deterministic. So we know exactly after how many cycles the command would be executed and how many clock cycle will take to transfer the data to propagate data through the switch. So we have short packets. It's like it resembles more like what's the name of this computer interface for the distributed I/O? Never mind. So it should have short packets. So it simply looks like more like register reads and writes than like Ethernet packets. So it uses it propagates the timestamps. It propagates the time. You are able to adjust the phase of the clock. So if you have several nodes, the phase of the clocks in each node is the same with some picosecond accuracy. We have quite well. This is the setup we built just with 2 FPGA modules, and this is what we get. But this is the older version. Now we improved. We used better oscillators, improved it to something like 5 times the phase noise. We got rid of these peaks, most of them. With new implementation, we have much better Scilabs oscillators, which are used.
So what sort of connector does it use?
Use SFP, standard. standard telecom the WDM single link. We need single link to have the same distance. And so we use the same hardware as for white rabbit, but we are running at 5 gigabit instead of 1 gigabit. Actually, now white rabbit is switching to 10 gigabit. So we can also run at 10 gigabit, but we don't need. It takes much longer to compile the cores, FPGA cores for 10 gigabit, and we don't actually use. But the hardware is characterized for 12 gigabit per second of the hardware we built.
So I have more maybe on the physics or quantum physics side. So you mentioned in particular in the context of ion traps that those quantum computers are as good as lasers are and electronics are. So what are the critical parts in this electronics that affect
Yes.
yes. systems, and like, do you know how it manifests? In what?
Actually, it's more complex. Electronics is also the magnetic field stabilization system. If you want to have some good fidelity, you need to stabilize your magnetic field to some picotesla, or even a fraction of picotesla, which is not easy, because you have this 50 hertz noise everywhere. So you have to compensate. You need to shield it. That's why we are using superconductors, just to provide very, very stable and good shielding and good and stable magnetic field. So this is one thing, very low magnetic field noise. Then we have photon. We have lasers. You need to have very precise. It's okay. You take a sample laser pointer. You know what bandwidth of the signal is? A few tens of gigahertz, even hundreds of gigahertz. No, tens of gigahertz. And then we need to narrow down to fraction of hertz, billions of times, to make this computer working. And it can be more precise, because the more precise, the more narrow the bandwidth is, you have the better physics. You cool the atom better. You address with better efficiency. Yes, when it's drifting, so it's working. The physics is working only for the moment when when the frequencies match. When it's not drifting, it's working all the time. So that's why most of the electronics is used to stabilize the lasers. You need to stabilize frequency. You need to stabilize the amplitude independently. And then you have a fiber. I mean, a fiber also generates noise. So we have also circuits which remove the fiber noise. So we have a photodiode. We have another circuit which simply measures the fiber influence, the vibrations absorbed by the fiber, and cancels them. So most of this hardware is, and then you have another thing which is the noise on the ion trap electrodes. With existing electronics, we managed to go down to 1 nanovolt per square root hertz, but it can be, I mean, the lower the better. Actually, what we are lacking is a good model of how the noise translates to the fidelity. And this was the task I wanted to work with you on, to create theoretical model of the noise propagation to the end fidelity. I know how to model the noise of the electronic circuit. I can describe with differential equations. But then there's some physics which needs to be, because this atom is sensing this magnetic field disturbances. And then what I'm missing is how to translate this model to the noise model of the noise to the let's say, for example, photon to photon interaction efficiency. I mean, atom to atom. Yeah. So this is what we are fighting now. That's why we want to build ASICs, because with ASICs we can go to very close to the ion trap. With existing electronics, which is simply located in a nearby rack, and you have cables, and these cables are transmission lines, and they are picking the noise from around. So the room in which quantum computer is located needs to be quite well shielded, placed underground on a dedicated how to say, foundation. The same with electromagnetic field. Every mobile phone, every BTS is broadcasting, and we are picking this noise. We are talking about nanovolts, so hundreds of picovolts. So you need to, if you have it in the same place as ion trap, you don't have this issue. You don't have this issue. Another issue is the number of vacuum feed-throughs. If you vacuum feed-throughs, I mean, feed-through is a piece of hardware which simply passes the signal via metal wall but isolates from high vacuum. It's not easy to make it. They are big. If you have a 100 qubit ion trap, the ion trap is this size only because you have a lot of these wires. If you place the ASICs to the ion trap, you simply replace 400 wires with 4 wires. And then you also you get rid of the cables. And if you to transfer energy through the cable, you need to consume power. If you get rid of the cables, you lower the power consumption a lot. So there are all the benefits. And of course, if you designing, because there are some attempts to design such ASICs, but people try to integrate them with ion traps. Of course, made this trapping process much worse. You want to build as a modular platform when you can connect several ASICs using base boards and then attach to the ion trap. And this is which is going right now. Yeah.
So one basic physics question. So how do you realize qubits in using trapped ions? And what is the readout? What sort of physical property you read on out?
This is somewhere shown here. We use this process. So we use two different. What's the name? This it's subtelne. No. The process przejście subtelne. Fine structure. Yes, you have two levels of fine structure, which you are able to. You need 2 pulses of laser to go to one of this stage, and you need another pulse sequence of lasers to go to the other stage. And to read out, you have another sequence of pulses which shine on atom, and if it's in one state it shines, and if it's in another state it doesn't. So that's why it's simple, because essentially you can take your camera and you can take a photo of qubits, and the ones which are ones during readout they are glowing. The ones which are zeros, they are not. So it's very, very simple. There's one photo of my colleague taken at the Oxford with his DSLR camera with just one ion shining in the ion trap. And Oxford has nice technology that they can actually use. They use electric field to switch between the states, so they need much less lasers than IonQ needs. So they are working on it right now. They have a publication on the best qubits. They managed to achieve 99.99% of fidelity on 2-qubit gate recently. I mean 2017, I think. And with this group, we are working on building this stuff.
Cool. Any more questions? I think that already arrived, but yes, maybe last question.
I'd like to ask, for how long could qubits remain entangled in this approach?
Well, I don't know exactly the response, but it's. I mean, the ions stay forever. Once you trap, it stays there until it hits with some residual gas. The qubits, I mean, can be. I believe it can be order of second. A few seconds, yes. But you cannot really compare them with superconducting qubits, because the operation rate is much lower. So you do operation with some millisecond scale instead of hundreds of nanosecond scale. But still, it has much longer coherence.
And what about the crosstalk between the qubits actually? Because in the architecture of superconducting qubits, usually you are trying to avoid situations that you have 4 qubits connected together because of the crosstalk. And how the crosstalk is created is actually let's say saved here.
Well, you have in this it's much easier to fight low frequency crosstalk than a high frequency crosstalk in case of ions, because the crosstalk is as good as the optics is. So if you need to have a good precise enough optics that it simply hits one ion. And since ions are separated by something like 50 to 70 micrometers, the crosstalk can be quite low. And especially with integrated photonics, when we connect the fibers directly under or over the ions, we can have very, very low crosstalk rate. I cannot say precisely what the crosstalk is. I have to ask our physicists. But it's much easier to control than in superconducting qubits. Because in RF circuits, in microwave RF circuits, it's really, really difficult to fight RF signal crosstalk. Which also, because this superconducting qubits, they are just resonant circuits with Johnson junction. Johnson, sorry. And they are just electrical circuits, which then simply like tiny antennas. So they also always have some crosstalk. Here, the atoms they can be separated, especially if you build a 2D. I mean the CCD, the next level, which is CCD, charge coupled device ion trap. Where is this? It was somewhere here. Somewhere? No, it was beginning. So we can simply separate. You can separate, for example, the memory zone from the operation zone. This is example. I don't have example of this Hoya trap, which is solved by called Quanta. The last one on the last photo, there was this Hoya trap, which has 2 zones. One is processing zone. I don't know. You won't see if you Google Hoya 2 ion trap, you can see there is some slit, and there are 2 zones. One is in these zones you do operation, and in the slit you store the atoms, the ions. So you can simply make operations, shift them, and they are not affected by the lasers.
Yeah, but the resonance frequency for the ions actually are very similar, so it's quite hard to control this.
I mean resonant. I mean, what do you mean resonant frequency? You mean the optical frequency? Yeah. But it's easier to specially separate light than electromagnetic waves. I mean, of course, light is an electromagnetic wave, but it's easier to simply take a piece of metal foil and then light stops. And in case of electromagnetic, it's simply one piece of metal foil won't harm unless you engineer it properly.
For the after class. So let's thank once again Grzegorz. So maybe just a few words about the next meeting. It will happen in March, 23rd of March, and we'll have 2 speakers, but they will give a joint lecture. Piotr Migdał and Klementyna Jankiewicz. The title will be Quantum Game with Photons to Tensors in TypeScript. The meeting will be probably in KMD. It's another location. It will be our new host, but I will confirm it later, so stay tuned. So thank you once again for your attention. We would also like to thank our host and sponsor today, Coodecool, and strategic partner, Daftcode. Remember to stay in touch and join our channels on YouTube, Facebook, and our mailing list. Thank you. Yes.
Sorry to butt in, so a little bit of advertising. On the same day, 23rd of March, I'm from ICM, University of Warsaw. We will be running 6th edition of Supercomputing Frontiers conference, a very unique, extremely high level, and the focus is on frontiers. So you might there be able to see really outstanding new things. And one of our speakers that might interest you in this particular group will be a fellow from Stony Brook and Brookhaven National Labs, who built the largest real quantum computing network. So that will be on 25th, 23rd, 24th, 25th March, and there are lower registration costs for students. You're all welcome. Check out our website, supercomputingfrontiers.eu. There will be some very neat things about neuromorphic circuits realized by quantum nanowires and so forth. Really interesting stuff. And things related also to calculations in nanocontacts. First talk will be about that in this.
There will be also tutorial given by Jarosław Miszczak. I've already posted information about the conference on our Facebook group, and I can also highly recommend the conference. I was also a speaker last year, and I talked about our quantum computing group here in Warsaw. And this year, Dr. Jarosław Miszczak from Gliwice, he also sometimes attend our meetings, will give a workshop. It will be introduction to quantum computing based on Qiskit, I guess, from IBM. So you can learn. We already organized the first workshop on programming Qiskit last year in May, and that will be the second workshop in Warsaw, and also more or less on the same time, but I think that 2 or 3 days earlier, there will be a similar workshop in Wrocław, and also one person from our group, Oskar Słowik, he was a speaker 3 months ago, will be giving a workshop on introduction to quantum computing on an example of Qiskit. So yeah, you are invited to attend, and I highly recommend all those events. All right, I think that's all for now. So thanks once again, thanks for coming, and I hope to see you next time, and it's time for after party.